Okay, so, ready for another good day?
Of course.
So ready.
All right. Any questions before we get going? No? So homework's due when?
Tuesday.
Tuesday. Okay. 4 big problems, really tough. All right.
Number 2 was easy.
I know, they're not tough. Okay. All right, so we've been talking about reflection and refraction. Can you grab that door there, Carlos? Just shut it down. So last time we talked about normal instance, and then we talked about oblique instance. And so we're basically trying to understand what the Fresnel equations mean. And with the oblique instance, we saw that there were some interesting phenomena, namely that at grazing instance, all surfaces look like mirrors. And we saw that we can get total internal reflection if we're in a medium of higher index going into a medium of lower index. So we go past a critical angle, then all of the light gets reflected. And we saw there was Brewster's angle, so we'll explore that today. But we want to go back to total internal reflection, and we were looking at evanescent waves. Yeah, let's.
When we said that at a grazing angle, everything acts like a mirror, is that assuming a very flat, perfect?
Yes, flat surface.
It's just where it doesn't, the index doesn't matter at all.
Yeah.
The roughness would matter if there was some.
Yes, and roughness will cause scatter. Yeah, which, so if you have a surface, then there's the specular reflection, and then if the surface has some roughness, then there's the scatter
Yeah.
from the roughness. And the scatter will be polarization dependent. Okay, so we were looking at a situation where we have the interface between two materials with N1 greater than N2, and the transmitted wave vector, KT, is at some angle theta 2, incident wave vector at theta 1, and then reflected wave vector at theta 1. And we went through and formally wrote down what the field is for the transmitted wave for the case of theta 1 greater than the critical angle, so, or equal to the critical angle. So we have then that we're in total internal reflection. And what we found is that the total complex representation of the electric field, so R and T, is equal to the constant complex vector ET times e to the minus beta z e to the j omega t minus k2 x n2 over n1, or rather n1 over n2, times sine of theta 1. And so Snell's law, n1 sine theta 1 is equal to n2 sine theta 2. We basically use it to get rid of theta 2 and write everything in terms of theta 1 here. And beta, we saw, was equal to k2 square root n1 over n2 sine theta 1 quantity squared minus 1. Okay, so what we need to do now is explore what this thing means. So this is an evanescent wave, which is an example of an inhomogeneous wave. So a homogeneous wave means that the surfaces of constant phase are parallel with the surfaces of constant field or field amplitude. wave is the surfaces of constant phase are orthogonal to the surfaces of constant field. What does that mean? So what that means is that if we look at our interface between N1 and N2, our phase is given by what's up here in the complex exponential. And so what would a surface of constant phase look like? This is our z direction, this is our x direction. So what must x be in order for this to be equal to some constant? Like what if we took this and set it equal to pi? What would x be? So we could solve for it, right?
Yeah.
And it'd just be something, whatever it is. So we could plot that surface like that. It's basically a surface where x is a constant. In order for this to be a constant, that has to be a constant. So that means the surface of constant phase is going to have constant x. Since that's the x direction, that's the surface of constant x. So whatever z is, doesn't matter, x is the same. So that means we have surfaces of constant phase that go like that. In what direction do they propagate?
Z.
Z is that direction. What does this say?
Negative.
Y positive x direction.
There's a negative sign on the second point.
Yeah, so basically, all of this, in order for it to be a wavefront, all of this has to be a constant, right? So if time increases, that means x has to increase to keep that a constant. So that means it's propagating in that direction. Okay, now, what about surfaces of constant field? So basically, the magnitude of the electric field, what would a surface of constant electric field magnitude look like?
Well, the electric field has to be orthogonal to the direction of propagation, right?
That's worrying about the polarization. We're just looking at the magnitude of the field. So if we take the magnitude of this thing, complex exponential goes away, right? We're just left with the magnitude of that, e to the minus beta z. So let's say we wanted a surface where this was 1 over e. Then that would have to be a surface for which z was a constant. If z is a constant, then that surface would look like this. If we chose some other value for the constant, for the magnitude, it would be like this. So those are the surfaces of constant field. And they're orthogonal to the surfaces of constant phase, therefore we have a homogeneous wave. For a homogeneous wave, they're both in the same direction. Okay, so
So the surfaces of constant phase don't change with evanescent or regular waves. those surfaces stay the same.
Right. Exactly. Yeah, so if you look at this thing, this wave then is propagating in the x direction, and it's decaying exponentially in amplitude in the z direction, which is a weird kind of wave. But that's what an evanescent wave does. So any questions?
So each of the blue lines represents a different amplitude of field, instead of exponentially decreasing.
Exponentially decreasing. So we could say this is 1 over E of the initial field, 1 over 2E, 1 over 3E, whatever. We could choose whatever we want.
So, this is the case of total internal reflection, right?
Mm-hmm.
But I'm still having a hard time understanding how there's total internal reflection and there are waves on there.
There's still a wave over there.
Yeah,
Okay, so this wave, what direction does it propagate?
X direction.
X.
Opposite X direction.
So it doesn't propagate in that direction at all.
Okay. Okay, so it's just the fact that it doesn't propagate in that direction at all. Okay.
There's certainly a non-zero power density over here, but it doesn't propagate into the material.
Okay.
Yeah. And then if you do an analysis of the instantaneous power transfer, instantaneously the power oscillates back and forth across the interface. But if you take the time average, it time averages to zero power propagating over here.
So this isn't loss at all.
No, no loss.
It's just power that is kind of sloshing across the boundary, but it all comes back in.
Yes, exactly. Exactly right. It sloshes back and forth enough to set up this exponentially decaying field that propagates in the x direction. Yeah. Okay.
I have a question.
Mm-hmm.
Is it this field that gives rise to the reflection, or is it the reflection that gives rise to this field?
Well, so what's going on at the boundary?
Well, so the field has to be continuous across the boundary.
Mm-hmm. Yeah, the transverse component of the field continues across the boundary. So because that boundary condition, we have to have a field over here, even though no power propagates in the z direction.
So I understand that.
Mm-hmm. Yeah, it's a weird kind of thing.
I guess I'm kind of wondering, yeah.
Yeah, those sneaky Maxwell equations. That's
So
what it
this-
sets up.
Is this true for like light and other general?
Anything, any electromagnetic wave.
So this is happening on like the side of a horn antenna or something, and that's with you?
Yes, depending upon the materials. Yeah. So with the horn antenna now, you've got metal, so you've got to do the boundary conditions for metal. And the boundary condition for metal, if it's a perfect conductor, is there's zero field inside the conductor. So if this is a metal, there's zero field over here if it's a perfect conductor. Which means that the reflected field transverse component has to be exactly opposite to and cancel the incident field transverse component. So that there's also zero total field on this side of the boundary. So that's what happens with the metal. Well, I mean, with the metal, you have finite conductivity, so the field isn't exactly zero over here, but it's small. And then you end up getting exponential decay of that small field, which gives rise to the skin depth phenomena. That's where it's coming from. Because you're basically creating a surface current over here. Okay. So another example of an evanescent wave that you're at least somewhat familiar with is if you have a fiber and you have light propagating down the fiber, and this refractive index is bigger than the core or clad refractive index, then if you plot the magnitude of the electric field in this direction, I mean, the electric field is transverse, but if we just plot the magnitude, then it's gonna do something like this. And then it's going to exponentially decay here. In other words, these regions, those are evanescent rates. So it's basically, this laid over on its side. So we're propagating in this direction along that boundary.
But the field is now 90 degrees off of what it was on the outside versus the inside.
No,
The
no.
field front,
Or
or the field surface, I mean.
so you mean this?
Yeah.
Yeah, so it's exponentially decaying that way. But the electric field direction,
That's not
the
the
polarization, then it depends. But, if this is the direction of propagation, if it was a plane wave, then we know it'd be in this plane. So we'll just leave it at that for now.
So sorry, one more. So like, since it's exponentially decaying, it's not that it's zero there instantly, it's that it decays and goes to zero. And then
Far away. Yeah.
far, okay,
Mhm, yeah.
okay.
Yeah. Okay. All right. So it turns out you can make use of this exponentially decaying field, and it gives rise to this phenomenon called frustrated total internal reflection. So if I have an interface here between materials N1, N2, N1 bigger than N2, and I'm instant at an angle greater than the critical angle, then in general, I get all of the light reflected from that interface, but I have a non-zero field here. So that means if I brought another interface up in here, like let's say I stuck an interface right here, separated by some distance d, or actually let's call it L, then as I take that interface and bring it closer and closer and closer to that interface, I start sticking it into that evanescently decaying tail. And if I get it close enough so that, we're not at e to the minus 100, we're at e to the minus 1 or e to the minus 2 of amplitude, what happens is we have to match the boundary condition here, right? And if we match the boundary condition here, that gives rise to a propagating wave over there. So we've frustrated the TIR. And it turns out this is exactly analogous to quantum mechanical tunneling. We basically tunneled across the gap.
So is it,
What?
So I was just gonna ask, if we were to do analysis of the total power, the reflected wave does not have the total power.
Correct. So the power is split between the reflected and the transmitted wave.
So what is it, when it says total internal reflection, it just means total internal field reflection?
This is
not power?
frustrated total internal reflection.
But I guess if we weren't to have the frustrated, we just have the other one. The sum of the power, we still have to include the power inside
Oh,
of the
so
material.
over here, all of the power coming in is reflected.
You know there's a field on the other side?
Yeah. It carries no net power in that direction. Yep.
So then essentially, as we increase L to infinity, we approach the actual total internal reflection.
Yep. Yeah, so one question is, well, how big would L have to be? Well, we could easily estimate it. So let's say that N1 was glass, N2 was air, and theta 1 was, say, 45 degrees. We already calculated the critical angle for this case, which is 42 degrees. And so to understand, how big of an L matters, all we've got to do is calculate beta, because this exponential decay goes as beta. So if we plug in and calculate, what we find is beta is equal to 4.4 inverse microns, which means the depth, z, at which the field is 1 over e, meaning that z. If z is 1 over beta, this becomes e to the minus 1. So we have e to the minus 1 of the magnitude of the field. So 1 over beta, and that's 0.227 microns. So about a quarter of a micron. So if we're 5 microns away, will we get any frustrated total internal reflection? Yeah. Because we're, what, 20 beta away? I mean, 20 of these away? I mean, there's pretty much no power there, e to the minus 20. So to get frustrated total internal reflection, in this case, we've got to be, you know, a quarter of a micron or less, really, to get any reasonable amount of power. If, on the other hand, we set theta to be 85 degrees, so we're coming in at a really small grazing angle, then beta is equal to 14 inverse microns. So the 1 over e distance is about 71 nanometers. So you got to get really close to get frustrated total internal reflection. So
it's most likely at the critical.
yeah, so you have the deepest penetration of this field at the critical angle. Yeah.
So what are the applications of frustrated total?
I'm going to show you. So first of all, I'll just tell you one. Actually, I'll tell you a couple. So if we wanted to make a beam splitter cube, not really polarization dependent, just a 50-50 beam splitter cube, how would we do it? We just do this. So you basically have a small gap between the two glass pieces. Now you've got a beam splitter. Another situation is some of you have done some slab waveguide work, like in lithium niobate. And so you do ion exchange or titanium indiffusion, but you end up with a slab waveguide. And then the question is, how do you couple power into that slab waveguide? And you could do end-fire coupling over here. So you could focus down light into the waveguide that way, which is kind of a pain. You could bring a fiber up to it, but with the fiber you've got a terrible mode mismatch, because if you're using single mode fiber, then the core is 9 microns, and this is, you know, maybe a micron and a half, 2 microns, 3 microns. So you have really poor coupling efficiency. So another way you can play the game is you could stick a prism on top of this and tune things so that you come in at an angle here so that you get total internal reflection at that interface because of this air gap. But you press on this and you squeeze the air there so that the gap gets really small. And you have this angle be such that your surfaces of constant phase, namely the red ones here, are the surfaces of constant phase for the propagating mode in that waveguide. And now you're mode matching the evanescent wave to the waveguide. And so you can get high efficiency coupling into the waveguide. And that's prism coupling. That's how it works. It's based on frustrated total internal reflection. And it works great. You can get pretty high efficiencies that way. Okay, and I'll show you some other examples from some of our papers actually, but let me just motivate a couple of other ones. If you have a waveguide and you want to couple light into another waveguide, I mean, you could do a Y junction, but alternatively, you could take your waveguide and do this and take another waveguide and stick it right up close to it. And because the waveguide has an evanescent tail, if that evanescent tail goes over into that waveguide, then you can get coupling of light from one waveguide to the other. Wow. Or these could be fibers. You have to get rid of the cladding, but you could do it with fiber as well. For people who do disc-based ring resonators, that's how you couple into the ring resonator, is by basically you've got this ring resonator and you want a whispering gallery mode where the light is bouncing around, on the inside of this disc. And how do you do that? Well, you can bring a tapered fiber here so that the evanescent tail overlaps here and couples in. If you're doing ring resonators, so you have a waveguide that looks like a ring like this, then you could bring another waveguide up close and get coupling into the ring resonator that way. You can outcouple by putting another waveguide here, outcouple light. So it's all based on evanescent coupling.
So with this, I don't know what a ring resonator is, but if that was like a fiber loop or whatever, could you like put light into it and then take your fiber away and light would be trapped forever?
Yeah, it'll decay slowly. It depends on what the Q factor of the resonator is to how long it would stick around. If it's 10 to the 4, then it would last 10 to the 4 round trips before it decays, by about half.
So this would be like fractions of seconds.
Oh, really tiny amounts of down picosecond range. But if you have a Q factor, say 10 to the 8, 10 to the 9. But really, what these things are good for is wavelength filters. So if you have a wavelength, or if we pause the function of wavelength, what the transmission is into this thing, then basically it's really sharp. If it's 10 to the 4, then this is super narrow. So what that means is that if you were to, say, put some antibodies on here, and those antibodies capture whatever antigen they're specific towards, then that can be enough of a refractive index difference for the effective index of the mode supported by the ring to cause a shift in wavelength. And then you've got a biosensor. So that gets used. I mean, they're exquisitely sensitive. I've seen data where you can actually see the capture of one molecule of antigen with these things. Really sensitive. But of course, when they're really sensitive, what does that mean?
Can't manufacture them.
Yeah, they're really twitchy. So they're highly temperature sensitive. And in terms of manufacturing repeatability, kind of forget it. Which means you have to make them tunable. If they're tunable, then you can tune out all the imperfections. So then that's another game you play. So, okay. All right, now let me describe another phenomenon based on this total internal reflection that's kind of a weird one, and yet is real, has been measured, and in a moment I'll show you some stuff that we've done with it in the past. So this is the so-called goose Hanschen shift. Any of you heard of that before? Okay. So to set it up, consider an interface. And let's say that I have just this really narrow beam instant on the interface. And I have the situation where this instance angle is bigger than the critical angle. So I'm going to get total internal reflection. The question is, where does the reflected beam emerge from the interface? And it turns out that, I'm going to highly exaggerate this and then correct myself when we're all done. It turns out it doesn't get reflected right there. It gets shifted. Here's where the exaggeration comes in. So there's a lateral shift, call it little d, along the interface at which the reflected beam comes out.
Is that like from a phase delay on the evanescent side or something?
Yeah, we'll get there.
Oh.
Yeah. Okay, and that is the goose tension shift. And you can calculate what that lateral shift is for TE polarized light. It's equal to 2 over Q tangent theta 1, and Q is equal to K1 times the square root of sine squared theta 1 minus sine squared theta c. For TM polarized light, then that lateral shift is equal to the shift for TE polarized light divided by the square root of sine theta 1 over sine of theta c, quantity squared, minus cosine squared theta 1. So the shift is actually different for TE and TM polarized light. And you can think of what is going on as, if I extend these guys back here, like this, it's like the light is being reflected from a buried interface at distance capital D behind the actual physical interface. And you can calculate the depth of that virtual interface. And for TE polarized light, it's 1 over Q. For TM polarized light, it's the same as TE polarized light divided by square root sine of theta 1 over sine of theta c, quantity squared, minus cosine squared theta 1.
What did you call this big D again?
It's the virtual surface from which it appears the light is being reflected. And it turns out that that surface is the 1 over E decay point of the field. Okay, so that's kind of wild. But the fact that we have this evanescent field in medium 2 with some non-zero field is really what sets all this up. So it looks like the reflected light is shifted. Now, we've already got an idea of how big D is, right?
Very small.
Yeah, really small. You know, maybe a few hundred nanometers. Yeah.
So is this only true for total internal reflection, or is this shift true also for just the reflection and there's still transition?
Only total internal reflection, where we're setting up this evanescent wave. Okay, so we know that this is maybe a few hundred nanometers. So if that's a few hundred nanometers, what's that? Also really small. A few hundred nanometers. So this would imply that I've got a beam maybe a few hundred nanometers wide in order to draw it like this, which is not correct. I can't have a collimated beam that small. We've got diffraction effects and everything else. So really what's happening is if I have a beam instant on an interface, then I'm getting a shift that's just a tiny little shift between the instant and the reflected beams for any normal kind of beam. And so then you may say, well, okay, what's the big deal, this Goose-Hampton shift, if it's just this tiny little thing? Well, it is real, it is measurable, and you do have to take into account in some situations. And so let me give you an example of a situation where we had to take it into account. So any questions before we do this? Yes, no? No? Want to turn that down? Oh man, they switched it out again.
If you're expecting a certain length of fibers and continuing every day.
I know. Yeah, that actually happens. In fact, that's where it's easiest to measure. Although there's other situations where it's really important, and I'll show you one right now.
Does this have anything to do with dispersion in the fibers that we
Yeah, some.
But it's not like the primary cause of that.
Yeah, I mean, you can measure the effect in fiber, but it's not necessarily the main thing that you worry about. Let's see, someone want to hit the lights back there? Okay. Okay, so let's see, let's go to this paper. Okay, so here's one of our papers, 2006. So we're doing something with polymer waveguides, and we've got these single air interface bends. What the heck is that? So we were doing polymer waveguides with something called PFCB, perfluorocyclobutane, which is a fluorinated polymer, so it was really nice for some waveguide applications. And so we have this buried core in a cladding, and so the core has a refractive index a little bit higher than the cladding. Now, whenever you have a waveguide and you try to make a turn, the minimum radius turn you can make is set by the difference between the core and the clad refractive indices. And typically, for polymers and glass waveguides and whatever, that core-clad difference in refractive index is really small. It could be on the order of 10 to the minus 3 in refractive index units, or 10 to the minus 2, which means your minimum bend radius could be centimeters. So if you're trying to create a little tiny chip with a sophisticated photonic circuit on it, and for one bend it takes a centimeter bend radius, well, forget it, it's never going to work. So what we wanted to do was be able to take materials that have low refractive index contrast between the core and the clad refractive indices and make really tight bends. And so what we did was, to make a tight bend, we would etch into the material to create a surface at which we can get total internal reflection. And so here you can see we've got a bend angle of 45 degrees. And it turns out that we had to position that interface. Let's see if we, maybe I don't have a figure on this one. I guess it's here. So placing that interface to get high efficiency came down to accounting for the Goose-Hampton shift. If we didn't account for the Goose-Hampton shift, then we wouldn't have as high efficiency on our bend. And so, long story short, we made waveguides with different numbers of bends so we could measure loss. And the fabrication process was unbelievably tedious because we had to put gold alignment marks in the same masking level as our core, and that meant they got buried when we put the upper cladding on, and it just was a mess. And we were doing E-beam lithography, and so you get charging, so you have to put a metal layer down to take care of the charging, but it had to have a good contrast relative to the marks, but whatever. So it was kind of involved. But this shows one of these interfaces, and the core is somewhere over here. You can't see it. There's no way to image that with an SEM. And bottom line is it worked quite well. So there we had to take into account the goose tangent shift. Over here we did something very similar with silicon waveguides, but the silicon waveguide was a ridge waveguide. So the fact that this is a little bit taller than the surround means that light that's propagating in the slab sees a little bit higher refractive index than the surround. So this structure looks like a waveguide. But the refractive index contrast is small because the height difference is small. But here you can see the confined mode. And because of our application, this is how we had to do the waveguide. We could not do anything else. And so the refractive index contrast is small, which meant the bends were huge. But we're trying to make a little tiny chip with all this stuff on it, so we had to have a way around it. The obvious thing to do was, well, let's just etch a surface here and use total internal reflection to bend the light for us. And so we looked at some different geometries for how to do the bend. And we did some modeling, some finite difference time domain. We had to account for the goose tangent shift, so we ended up having a 70 nanometer offset in position to account for that, to maximize our reflected power. So we did, again, E-beam lithography, a bunch of steps. But this is what the etched surface looks like in relation to the waveguide. And here you can see that surface. It looks a little bit rough, but it's not too bad. And it actually worked quite well. So when I came here, I bought the STS reactive ion etcher for this work. So that's why we have the STS in the clinic.
Thank you.
Yeah. And so, we did loss measurements and yada yada. Okay. So then I'll just show you, let's look at this one. Yeah.
How did accounting for that shift, did it make it so you just had to make the etch larger?
So where the bend happened,
Yeah.
it was a matter of where do we put the interface in relation to the bend to account for that shift. Because if it was off, then the reflected light would not be matched up with the output wave. That would be off, and then we wouldn't get good mode coverage. So once you can make individual bends, then you can do the good stuff. And here we actually changed our bend angle to get better efficiencies, and we actually backfilled with SU8. So it wasn't air; it was SU8 in these gaps, and we created splitters. And splitters are operating just on the basis of frustrated total internal reflection. So we had to etch very narrow gaps in here. And I've skipped over the paper that talks about that.
How narrow were they?
70 nanometers for 90-degree geometries. And when we went to the 105-degree geometry, it widened out to, I think, 100, 105 nanometers. And that was easier to make than the 70 nanometer because we had to go, I think, 3/4 of a micron deep. So it just worked out better. So here we've got input waveguide, this beam splitter, which is just based on a narrow trench, frustrated total internal reflection. Here's an actual mirror. These little things, these random little holes, are to kill scattered light. Later what we did was we took the entire wafer except a band around the waveguide regions, and we doped everything but that band. And the doping caused the silicon to be very absorptive to our light, which is at 1.5 microns. So then we didn't need these scatters to get rid of light. And then this shows trench width, and then the efficiency for transmitted and reflected light as a function of the trench width. And it, bottom line is, it worked out really well. You can see there's an offset here, and that's because we were measuring the trench width just looking down, but it actually blew out a little bit in the depth of the etched silicon. Yeah.
So if you had made your waveguides wider, would it have gotten rid of the need to worry about the assumption?
We wouldn't know because we wouldn't have been single mode anymore. We had to be single mode. Yeah. And we were actually doing all of this because we had these micro cantilever arrays, and we were reading out the deflection of each cantilever on the basis of light propagating down the cantilever, crossing a little gap, and then getting picked up in this multi-mode structure we designed that has two outputs. So the output light depended upon deflection. And so we could measure down to like 15 picometer deflections. I mean, incredible. The best AFM results ever reported in terms of deflection measurements using a laser bounced off the end of an AFM tip. We could match that with our REACT method using the same thing. And we could do it across 32 cantilevers simultaneously. So it worked really, really well. And so here we've got a 1 input to 32 output, and the efficiencies are all within about roughly a factor of 2, 2.5-ish, which is perfectly fine for our application. So it worked really well. But interestingly, this, and this was 10 years ago when we published this, what we ended up finding is we put in all this effort to make this readout method, and I haven't shown you the half of it, to read out these cantilever arrays, which worked awesome. And then the biochemistry that we were using was based upon reports in the literature. Turns out those reports were wrong.
How'd you find that out?
Because we measured it because we could. I mean, our measurement system was so exquisitely sensitive. So we measured the effects that were reported in the literature to be quite large, and it turns out they were actually quite small. And so this reported literature was wrong.
Called now.
Sort of.
Publish your results.
Yeah, we published our results. So we basically spent literally millions of dollars. When I came here, I brought millions of dollars with me. And I spent $1 million in the clean room, to buy stuff. Well, it maybe turned 50K of it in the lab. And we spent probably 8 years working on this. And in the end, the published literature on the biochemistry was wrong. And so when we had a measurement system where we could actually do all this stuff, and I saw that it was really poor in terms of how much effect was there, I just pulled the plug and said, okay, we're doing other things. This is not worth it. So, and the funny thing was, we actually had a golden result in our measurements that we could have published and shown, the golden result. But I insisted that my students repeat it, and they had all kinds of problems and could not repeat it. And so we would publish it. So repeatability is crucial. You have to be able to repeat what you do. So so that was quite the experience. So yeah, pulled the plug and had to find other things to do. And now we're doing the 3D printing of microfluidics.
Does that happen often?
Let's put it this way: how risky is research? Very. Okay, so we're engaged. For those of us engaged in research, you can put the power. For those of us engaged in research, we're doing risky things. So how often do you expect to be successful?
Not very often.
Yeah, well, you never know. I guess what I'm saying is don't be surprised if you're not successful. Successful in the sense of achieving the result you're going for. You can be wildly successful in terms of learning new things, and really, as far as education is concerned, that's the name of the game for you. For those of us who have to keep the funding going, that's not an optimal outcome. But you know, research is hard. In fact, there's a paper I saw again after not having seen it for a number of years. It was published in the mid-2000s by someone, I think in microbiology, or maybe it was neuro something. But at any rate, and I don't remember the title, but it was something about the importance of stupidity in research. And his comment was that he had this colleague going through grad school who was very, very bright, brightest person he'd ever met, really. And this person ended up dropping out of grad school and doing something else. I think she became a lawyer and had a very successful law career. And he ran into her years later and asked, well, why'd you drop out? And she said, I just felt so stupid all the time. And he thought about it. He thought, yeah, I guess I feel stupid all the time too. But you know, he'd gotten to the point where that was just situation normal. And so you know, what does it mean to feel stupid? Well, I mean, you're banging your head against something that no one knows, and you're trying to figure it out, so you feel stupid.
And then when you figure it out, it's always something simple.
Yeah, you figure it out, and it's kind of straightforward in many cases, although it wasn't straightforward to get there.
Yeah.
And so in the course of his training, he got to the point where his satisfaction with doing research work was not wrapped up in him feeling brilliant, you know, every moment through the course of his day, but rather having those occasional flashes when everything comes together and you get it after maybe days or weeks or months of not getting it and feeling kind of stupid. But in the research endeavor, that's the nature of the beast. You know, you're trying to figure out things that no one has ever done before. Therefore, you can't just walk down the hall and ask someone, hey, I'm having this problem, it doesn't work, you know, what's going on? It's not like a homework problem in a book, which is what you get trained on during your education. So you kind of become used to or have an expectation that that's what it should be like. You know, you get a problem, there is an answer, there's a well-defined way to get there, and that's how it should be. Well, no, that's just practice so you get the fundamentals down. That's the only purpose that serves. It does not prepare you for actually doing real things. Doing real things, you're going to feel stupid because you don't get it, and you're going to be messing around until you do get it. But then when you do get it, it's awesome. It's very satisfying. So, yeah, so don't let feeling stupid dissuade you. Okay, so we've talked about TIR, evanescent waves, and the Gibbs-Hamilton shift. Now we need to say a few words about the Brewster angle, and then move on to our next topic. So, with the Brewster angle, what we saw is this clearly is present for TM polarized light in the interface. And basically, if we have two materials, and we have a transmitted wave, then what's happening is we have incident wave here and reflected wave. For light that's polarized in the plane, all of it goes through the interface. Nothing gets reflected, which is pretty nice. You don't lose any light at the interface. And so, if you go back to Snell's law and the reflection coefficient for TE polarized light, you have N2 cosine theta 1 minus N1 cosine theta 2 over the sum of the two. Basically, when RP is equal to 0, which is the condition for the Brewster angle, then the numerator, the N2 cosine theta 1 must be equal to N1 cosine theta 2. Now we can use Snell's law and eliminate theta 2, so we only have theta 1's. And if we do that and solve for theta 1, which then we call theta b, the Brewster angle, what we find is that it's equal to the arctangent of n2 over n1. And so that's true whether we have internal reflection going from a higher to a lower index or external reflection going from a lower to a higher index. It happens either way. And when that does happen, it turns out that this angle right here between the transmitted and reflected waves is 90 degrees. So
We say reflected, but there isn't a reflected, right?
yeah, there's a reflected wave vector, there's just no power going in that direction.
Oh, okay,
Yeah. So, so when we're instant at the Brewster angle, then the reflected and transmitted wave vectors are at 90 degrees with respect to each other. Okay. So it turns out you can use that effect to make a polarizer. There's something called a pile of plates polarizer, where you just have a whole bunch of glass plates at the Brewster angle, and when you have light come in, then any light that's TM just goes right on through all the interfaces. But TE, you're going to get a little bit of reflection at each interface. So if you have enough interfaces, you get a lot of the TE light reflected out, so it's no longer the beam. So if you just have a whole bunch of glass slabs, you can make yourself a polarizer that way. Just using the Brewster angle effect. Okay, well that's it. Any questions about any of this reflection and refraction stuff?
Is there a shift when the wave is reflected and it's not a total internal reflection? Is there a shift or there is no shift? Like the
No shift.
No.
shift. Nope. Okay, so now we're done with reflection and refraction, at least for the moment. And we need to move on to our next topic, which is interference. So interference, we're going to break it up into two sort of categories of interference. The first is when we just have two beams, and we're looking at interference between those two beams. And then the second, later, we're going to do arbitrary numbers of beams. So if we understand the two-beam interference case thoroughly, doing the arbitrary number of beams is going to be a generalization that will be relatively easy to understand. So let's start with two-beam interference. And basically what we're going to say is, hey, let's use the electromagnetic model, and let's use plane waves, which by definition are monochromatic, i.e. the simplest possible thing. Let's figure out what's going on, and then it's easy to generalize from there. So let's say we have a beam with wave vector k1. So we've got this plane wave propagating, and another beam with wave vector k2. So we've got a plane wave propagating in that direction. And what we want to know is, what is the total field in this region of overlap, and what is the power flow in the region of overlap? So in either case, we have to start with the fields. And you're going to see a common theme here. You always start with the fields. And so what we need to do is write down the complex representation of the two fields. So let's write it as E1 and E2 of R and T. And so this is a plane wave. It's monochromatic. So in general, the spatial dependence will be in this complex vector, and we'll have e to the j omega t. And likewise, we can write the same functional form for the second wave. And then this spatially dependent vector is, because it's a plane wave, has a very particular form. And we're going to write, as usual, we're just going to leave the spatial dependence implicit. And so we can write it then as some constant complex vector, call it E10, e to the minus j, k1 dot r. So just the usual thing for a plane wave. And so the complex amplitude vector for the second wave is going to have the same functional form. So constant complex vector E20, e to the minus j, k2 dot r. And now K1, the wave vector for the first beam, let's write it as the wave number times a unit vector in the direction of propagation, u1 hat. And K2, we can also write it as having the same wave number, because we're assuming they're the same frequency, but a different unit vector in terms of direction of propagation. So, since I have the functional form for each of the fields, it's easy enough to write down the total field. So the total field, the complex representation of the total field, is just going to be this complex representation plus that complex representation. And so if I write those down and collect the common complex exponential, I can write it as E1 of r plus E2 of r, and both of those are vectors, times e to the j omega t. Right? So I've just plugged in these two and pulled out the complex exponential. And then I look at that and I say, well, gee, clearly I can write this as E total of r, e to the j omega t, where this sum I've just given a new name. And then keeping with our usual practice of leaving the spatial dependent, or having it be implicit, I drop the explicit dependence on r. It's just understood that it's dependent on r. And so this then is the complex amplitude vector for the total field. And I could do a similar thing for the magnetic field, for the electric flux density, the magnetic flux density, etc. Okay, so I just wrote down some math to say something pretty obvious, right? And the total amplitude vector is just equal to the sum of the individual amplitude vectors. That's really all I said. Okay, now, why did I bother to say that? We want to calculate the complex Poynting vector. And the complex Poynting vector is what? B cross H. Is that it all? Is that all of it?
Wasn't there another one, 1 over 2 eta of the magnitude?
Times squared.
So the complex amplitude, or complex Poynting vector is 1/2 the electric field complex amplitude vector crossed into the magnetic field complex amplitude vector, complex conjugate vector. But this is now for the total field. So this is the total complex amplitude vector, or the complex amplitude vector of the total field, and likewise for the magnetic field. Okay, so what we want to do is we want to calculate this. This is the complex Poynting vector. Why do we want to calculate it?
Will that give us a better shape of the addition of the fields or direction?
It'll tell us what the power flow is for the sum fields. Remember, the Poynting vector is all about power flow. So if we get the power flow for the summed fields, then we'll know what's going on with that power flow. So the Poynting vector will tell us that. Okay. So I have then what the complex amplitude vector is for the total electric field, I need the complex amplitude vector for the total magnetic field. So to get that, what I do is go back to Ampere's law, or no, Faraday's law, and with some manipulation, you can show that the complex amplitude vector for the total magnitude, or total magnetic field is J over omega mu naught times the curl of the complex amplitude vector of the total electric field. So, great, and I know what that is, so good. Now I just have a little algebra, and then I can substitute in here and have everything in terms of that electric field. So this then is J over mu naught omega, and then we have the curl of this thing, but that is just E1 plus E2 for the individual fields, right? And then, yeah, we'll get there. Okay, so that gives me J over mu naught omega, and then I can pull the curl through, so I have the curl of E1 plus the curl of E2. Okay, fine. Now, if I actually do these curls, so you see E1 is this, E2 is that. If I go and do the details for the curls, what I end up with is J over mu naught omega, and then the first curl becomes minus J times the wave number U1 hat cross E1 plus a minus JK U2 hat cross E2. So, do you know how I got there? So I just do this curl operation on this, and the spatial dependence is all right up in here, and I end up bringing down a minus JK, and I can pull the K apart as wave number times unit vector. Okay, so if I pull the minus J out, it's multiplying plus J, so that just gives me a plus 1. And then K, I'm going to get a K over mu naught omega, right? Because I can pull the wave number out. Yeah.
So then, is that E1, should it be E1 0?
Nope, it's that.
Okay.
Yeah. Yeah.
So is that still a cross then?
Yep.
Okay.
Yep. Still got a.
Oh, I see, you just decomposed the plural.
Yes.
Okay.
Yeah, so I did the partial derivatives, which operated on this, brought some
Gotcha.
things down, and then I just gathered them all back together to write it in a compact form. And I encourage you to go home and do it, just prove to yourself that's true. Okay, so K is omega over C times refractive index. That's mu naught omega, the omegas cancel. And then C, that is, well, this is 1 over C. So 1 over C, we're going to get square root of epsilon naught mu naught, this is times refractive index, over mu naught, right? Because C is 1 over square root mu naught epsilon naught. Okay, so I got square root of mu naught up here, mu naught there. So that's going to give me a square root of epsilon naught over mu naught times refractive index. And then the impedance of free space is the square root of mu naught over epsilon naught, right? So this is refractive index over the impedance of free space, which is just 1 over the impedance of the medium. So this is 1 over the impedance of the medium times U1 hat cross E1 plus U2 hat cross E2. Okay, so now I've got H total. And I want to calculate this. So what do I do? Yeah, I've got to substitute this in for that. It looks like you're going to be saved by the bell.
That was a 90s shit.
Yeah. So on Tuesday, what we need to do is take this, substitute it back in there. So I'm going to have this, which is E1 plus E2, crossed into all this stuff. It's going to give me a bunch of terms. So we need to go through term by term and see what we get. And then that's going to lead us to 2B interference.
Just a quick question. If I remember correctly in the homework, problem 4, I know it said something about a complex pointing vector in there.
Okay.
Do we actually know enough to be able to do that
Well,
problem?
let's just make the homework due on Thursday.
Cool.
And then there's no issue.
Okay.
Okay, so homework due Thursday. Everyone heard that, right?
Yeah.
Homework due when?
Thursday.
Thursday. Yeah, Carlos is not listening.